Okay, did anybody get a number for the extra credit for the final velocity of the boat? Anybody do that? Who did the extra credit? 2 people. Do you, Blair and Kat, do you remember what numbers you got?
I am going back and checking. Okay, I don't know if it's right, but I got 0.597.
That is correct.
Oh, nice. Okay.
That is correct. So let me work that out today before we move on to a new section. Just give me a second to get that up. Okay, so real quickly, just to remind you, what's going on. We had this boat. And we're stuck in the boat. And we have 2 stones. So the mass of the boat, which again includes not only the boat, but you, yourself, and all your stuff, everything but the stones, is 160 kilograms. And now the mass of each stone is 5 kilograms. And the speed of the stone relative to the boat would be minus 10 meters per second, because we're going to throw them, to the back. And so what we did is we started with initial momentum equals final momentum. And that's going to be the mass of the boat times the speed of the boat plus, well, technically we want to be careful because there's 1 stone still sitting in the boat. And then there's the mass of the stone times the speed of the stone. So this first piece is the boat plus 1 stone, and the second piece is the other stone. So that's going to be m boat plus m stone times b boat plus m stone. And using the same idea as last time, the speed of the stone will be the speed of the boat plus the speed of the stone, relative to the boat. And when we distribute this, we have mass of the stone times speed of the boat here, and the mass of the stone times speed of the boat there. So what we get is mass of the boat plus 2 m stone times the speed of the boat plus the mass of the stone times v stone relative to boat. Okay, so then we want to solve for the v boat, so we're going to move this piece to the other side. We have minus m stone v stone relative to the boat equals m boat plus 2 m stone v boat, and dividing both sides by the mass of the boat plus 2 times the mass of the stone gives us the speed of the boat. So I went through that pretty quickly because it's basically the same as what we did last time, with the only slight change is we got to stick another stone in the boat. So if we put the numbers in here, we're going to get minus 5 times minus 10 over 160 plus 2 times 5. If you would refer to what we did last time, the denominator was 160 plus 10, so the denominator was exactly the same. And the numerator was 10 minus a 10 times a negative 10. So the numerator was exactly half what we have here. So we get exactly half of the velocity we got from the previous case, which makes sense. We threw half as much stone, we get half as much velocity. However, when we throw the second stone, the story's a little different. So what happens when we throw the next stone is we now have a P initial. And the P initial is the mass of the boat plus the mass of the stone times the speed of the boat that we just found. So there's the boat plus one stone, all moving, and that becomes our system. And then on the left, we're going to have mass of the boat, V boat, we'll call it V boat final, plus mass of the stone, speed of the stone. So that's going to be mass of the boat, V boat final, plus mass of the stone times. We have to do the same thing here that we did before. This will be V boat final plus V stone relative to the boat. Left-hand side just kind of stays the same. And then if we want to combine terms that have the V boat final, putting those two together, we have mass of the boat plus mass of the stone, V boat final, plus mass of the stone, V stone relative to the boat. And that's what we have now. Left-hand side is the same. And what I'm going to do is I'm going to divide both sides by this thing. M boat plus M stone, M boat plus M stone, M boat plus M stone. Because when I do that, a lot of things are going to cancel. Those cancel and those cancel. And what we get then for our V boat final is just the V boat, which really kind of is our initial speed for the second part, or the final speed for the first part, minus M stone, V stone relative to the boat over mass of the boat plus mass of the stone. So I'm going to put in, just so we can make sense of what's going on before we actually put numbers in, what we had before. So this first bit is the boost we got from throwing the first stone. And what we have on the top is sort of a thrust, the mass of the stone times the speed relative to the boat. That's going to be that 50. And on the bottom we had the total mass of the system, the mass of the boat and both stones. Now when we do it again, we get basically another boost that's the same on top, just another 50. But on the bottom, because the mass of our system has gotten smaller, instead of 170 on the bottom, we have only 165. So when we work that out, that is, minus a 5 times minus 10 over 160 plus 5. Let's see what that is. 50 divided by 165. That's 0.56. One second. That's not right. It's 0.303. Just mispunched in my calculator. Why is my eraser not erasing? Okay, so that's 0.303, and when we add them up, we're going to get 0.597, which is what Blair said she got, and this is what we got previously. Okay, so it's a little bit faster if we split the stone in half, because the second stone, when we throw it, we get sort of the same size push, but the mass of the system has become a little bit smaller, if you want to think of it that way. Okay, so any questions about that? So I think that there's an obvious question to ask as a follow-up to this example. Once we see that taking that 10-kilogram stone and splitting it in half and then throwing them one after the other, once we see that that gives you a better final velocity, Can anyone think what the next natural question would be? No? So for me, this is how I think of it. If splitting splitting the stone in half gives you a faster velocity, wouldn't it also do the same if we took the two 5-kilogram stones and split each of them in half? So that instead of throwing a 5-kilogram stone, we throw a 2.5-kilogram stone and another 2.5-kilogram stone. And if we did that, wouldn't we have to get something a little faster than this number, 0.294? And when we do the same with the next two stones, wouldn't we have to get something a little bigger than this? And so if 4 stones is better than 2, wouldn't 8 stones have to be better than 4? And wouldn't 16 have to be better than 8? And so on. If we would keep splitting up the stone into smaller and smaller bits, it would have to give us a larger and larger final velocity. Does that make sense? Raise your hand if that argument makes sense to you. Okay. So the real question for me is, how fast could you go if you could just do this indefinitely? What if you could just turn the stone into sand and spray it out of the back of the boat with like a sand blaster or something? How fast could you get? And part of me, if I didn't know better, would say, well, gosh, since it gets faster and faster, the more you split up the stone, there would be no limit to how fast you could go. But of course, if that were true, someone would have figured out the sandblaster method of moving ships, right? Who needs a propeller or anything? You just have a bag of sand and you shoot it out of the back of the ship. So there is sort of a natural limit to that. It gets faster and faster, but it approaches a limit. And the formula would be the V-boat final would be equal to the speed of the stone relative to the boat. I'm not going to prove this, but because it requires some kind of fancy math to do it, but over the natural log of the initial mass over the final mass. Okay, so in our case, that would be minus a minus 10 times the natural log. The initial mass of the system was 170 kilograms, and the final mass, what's left after you get rid of all the stone, is only 160. And you get 0.606 meters per second. So we got 0.588 for one stone, 0.597 for splitting it into 2 stones, and 0.606 for infinitely many stones. If you notice, the difference between these is 0.009, and between these is 0.009. So basically, most of the effect you get would be when you first break that stone in half, but you get just as much boost by continuing this process infinitely. So why I think this example is interesting is because this is how rockets operate. Rockets do not have fuel and then just have one mighty explosion where they just shoot the fuel out of the back of the rocket. They have a continuous burn. The fuel is being ejected as, flaming hot gases at a certain rate. And that rate would be what we would call the speed of the stone relative to the boat, but it would be the speed of the exhaust. So speed of a rocket would be speed of its exhaust. And if we just use the magnitude, we don't need that minus sign, times the natural log of the initial mass of the rocket over the final mass. And so this is known as the rocket equation. Now, you will not have problems with the rocket equation, but I thought it might be able to, if you could go to a place and meet other people, then you could say that you were learning rocket science. But right now, that's not. It doesn't matter. I'll take it from me. It won't help your social life anyway. So, but you never know. Anyway, this is the rocket equation. If we wanted to take a rocket to another, another star, this is how we would figure out the speed of the rocket. And unfortunately, and probably some of you are not so familiar with natural log. I'm going to assume that probably many of you are not. But natural log is a function. If I graph the function, it kind of goes like this, and it gets bigger and bigger and bigger, but it gets bigger slower and slower. So just for example, suppose we have a rocket, and we just want to move this part, just that part. Maybe that has a mass m, and the rest of it has a mass 1,000 times as big. Okay, so that is all the fuel is 1,000 times as much mass as just the little bit where the astronauts are who want to go to the other planet. So how fast you could go? Suppose your exhaust was so the speed of the exhaust, that's always measured relative to the rocket, is 10,000 meters per second. That's really fast. Okay, so 10,000 meters per second. Then we have natural log. The initial mass would be 1,001 times m, and the final mass, all we're going to get to the planet or the other star would be just one mass, 1 times the mass. So if we do natural log of 1,001, that's only 6.91. So what do we get? We get 69,100 meters per second. So that may sound fast, but to get to another star, the closest star is 4 years for light to reach us from that star. And the speed of light, c, is about 3 times 10 to the 8 meters per second. This is 6.91 times 10 to the 4 meters per second. So light travels 10,000 times, well, really about 5,000 times as fast as this rocket, and it still takes 4 years. So multiply 5,000 times 4, and that's how many years it would take us. That's a lot of years. I think that's 20,000 years. So we cannot get to another star using a rocket. Using the technology that we have, we can never do that. It would never work. And it doesn't get better. You might say, oh, what if we have a giant rocket, so we have 10,000? So we have 10 times as much mass. If we put in 10,000, the natural log of 10,001 is only 9.2. So that would put us at 9.2 times 10 to the 4, but we're still not getting close to 3 times 10 to the 8. Okay, any questions about rockets? I have to tell you, as kind of a science nerdy kind of person, I was really disappointed when I learned that rockets are never going to get us to another planet, because I really want to see, I mean, maybe like Mars, but I want to see life on another planet. Oh well, that's just too bad for me. So that's just to wrap up the extra credit, and I thought it was kind of a cool example because it segues into how rockets work. Now, going forward, we are going to learn about some new physics. I'm going to give a little bit of an introduction here for the few minutes. And then the next chapter, in particular, this is going to be the chapter for those of you who are thinking about physical therapy or even some other medical type of field. This is probably one of the 2 most important chapters. If there's anything that's relevant to the human body, it's the next chapter. For those of you who are interested in the body, there's going to be, examples having to do with how the body works. And again, for physical therapists, this is probably the #1 thing you need to get out of physics class. But let me kind of set it up, because as we segue into the next material, we essentially, let me do a quick summary of everything we've learned so I can show you how the new material is going to fit in. So far, we have learned about kinematics. We have our master equations. If we want to write those down, V final equals V initial plus AT, and V final squared equals V initial squared plus 2A delta X. So that's kind of where we started. And we learned these equations, and then we learned the two-dimensional versions of the equations. And after that, we learned about Newton's laws. We said, well, we need to find the acceleration in all of these other cases. So we had net force equals ma, and we learned how to use that to find acceleration. Once we, I'm not going to write down every single formula, like, formula for friction and Newton's third law, but these are the key ideas. And after we did that, we found out about energy, work, which is, the force times delta x times the cosine of an angle. And we know that net work equals the change in energy. And we really, at first, we just had kinetic energy, okay? And then we kind of did some tricks where some of the works, we called them potential energy. But this is kind of the physics equation that's, the key idea. And, kinetic energy is given by 1/2 mv squared. And then we learned that net force is really equal to change in momentum over change in time, where momentum is defined as mass times velocity. And that's basically everything we've learned, okay? We finished 1/2 of the semester. I don't know if I made that point last time, but we're halfway done, which is, it's good, right? It's good that we're halfway done. And we've learned all this stuff. Now, to go forward, what we're going to do is we're going to focus in on all of the same physics, but we're going to start thinking about the fact that our objects have a size. They are not just point-like objects. So far, we actually pretended everything was a point-like object. So for example, when we say we push a box, we never worried that maybe the box tips over, or when the box is sliding down a ramp. It could start kind of tumbling down the ramp. That's because it has size. But we just ignored all of that. Nothing could rotate, nothing could do anything strange. So when we open the door for objects to have an extended size, so that it, for example, it matters which part of the object we push, then we have to go back over all this physics and re-evaluate it. Now, the key idea came when we talked about centripetal force, and we taught something that moves around in a circle with a radius r, and it goes through an angle theta, and we talked about computing the arc length s, where s is equal to r times theta. It turns out that that is the key idea that allows us to start talking about motion, as something spins in a circle, as it rotates. So the idea is that the arc length is what we would think of as a linear variable. That's basically like the distance if we are an ant walking around the surface of, an orange. Of course, we are basically ants on the surface of an orange. So when we're traveling from, say, St. Louis to Los Angeles, without realizing it, the distance we measure is really an arc length. So this arc length is kind of like a distance. So if you think of it as your delta x and the theta as maybe a delta theta, then this becomes sort of the key relationship to relate what I call linear variables, meaning moving in a line, versus rotational variables, so something that's rotating. And all we have to do to see that that's the key is divide it by delta t on both sides. because delta x over delta t is velocity. And that would give me r times what we can call omega, where omega is defined as delta theta over delta t. So velocity we know about, displacement over time. What is this omega? By the way, that looks like a curly W, but it's really the Greek letter omega. So I'll try to make it look, the way it looks in print on the book. It's going to look like a kind of a rounded W. It's called omega, and it's delta theta over delta time, which is change in angle over change in time. So we call this the angular velocity. Angular velocity. So we can relate the linear velocity to the angular velocity. And we finally can write delta v as r times delta omega and divide it by delta t, and we get a equals r alpha, where alpha, that's the Greek letter alpha, it looks like a A or like a fish, is equal to delta omega over delta t. So we again have a linear variable and a rotational variable. So these relationships here, if I would summarize them, delta x equals r times delta theta, v equals r times omega, a equals r times alpha. These are the key for us to take all of our linear variables and linear equations and translate them into rotational versions of themselves. I'm going to just move this down a little bit because I want to kind of have parallel equations going here. So if I want to take this equation and create a rotational version of that equation, all I have to do is divide the equation by r. If I divide it by r, we look over here. Delta x divided by r is delta theta. V divided by r is omega. A divided by r is alpha. So what it does is by dividing by r, it converts all of my linear variables like delta x, v, and a into rotational variables, delta theta, omega initial t, plus 1/2 alpha t squared. And doing the same thing for the next two equations, we'll convert them. Anywhere we see a v, we get an omega. Anywhere we see a delta theta, for example, we're going to get a delta x, we're going to get a delta theta. And so what we can do is we can take all of the physics that we've learned so far and we can convert them into the rotational version. So these are the linear equations. I like to think of those as Latin equations because they're all written with the Latin alphabet. The alphabet that we have, that we use today in English, is the alphabet of the Romans. So it's the Latin alphabet. And we're going to convert them into rotational equations, which I like to refer to as being in Greek. So we use the Greek variables for all of the rotational variables. So if we want to convert from Latin into Greek, from linear into rotational, we can do that. Now, for these first three equations, it just means dividing by r, or r squared in the case of the third equation. But for the rest of them, it's a little bit slightly more complicated. So let me pause and just talk about these guys first. So this is actually, from a student perspective, this is like the best thing that could happen to us, because you already by now really know how to solve the equations. I mean, you pretty much should have mastered that by now. And so when we go forward and we start solving problems about rotation, you don't really have to learn anything new except what these new symbols mean. But if you know how to translate a problem into math using these variables, you can very easily learn how to do that with the Greek variables. If you didn't fully get that when we did it with the Latin variables, then here's your chance to sort of solidify your understanding. But this is like a 2-for-1 special. We get double the equations for almost no cost. We have to learn very little in the way of new stuff. So for example, if we had a problem that said a car starts at 50 meters per second and accelerates at 2 meters per second squared for 5 seconds, how fast is it going? We would immediately kind of think, okay, we know the initial velocity, the acceleration, time, we'll find V final, right? And so the Greek version would be if we have something rotating at 5 radians per second and it accelerates at 2 radians per second squared for 5 seconds, what is its final angular velocity? So then we would just look at the Greek version of that equation. And in fact, you can map, when you read a problem, you can kind of think to yourself, okay, this is like the velocity, this is like the acceleration, this is like the time, I want the final velocity, so which equation over here would I use? And then that will allow you to know which equation on the Greek side you use. So you'll see this is kind of a bonus, a very nice thing here. Now, for the rest of these, and we have actually 3 chapters devoted to translating all the old stuff into new stuff, all the linear physics into rotational physics. So it takes a while to get through it all. And today I'm giving you a little bit of an overview, and then we're going to focus on only one special type of problem. So the rest of these, I'm going to go through them today, but we really will only be using one out of these, you know, what are there, 9 equations. And that's for this unit, okay? So the net force equals MA equation. Well, there's a Greek version of force, and it's called the torque. And we use a Greek letter tau. It looks like a T with a tail. And instead of the mass, we have I, and instead of the acceleration A, we have alpha. So the tau symbol is called torque. And the I symbol is called the moment of inertia. So it's an I to stand for inertia. This is the Greek or rotational version of Newton's second law, and we'll come back to it and talk about what exactly the torque and moment of inertia are, but basically the torque is the rotational equivalent of a force. What's a force? It's what you do to make something accelerate. What's a torque? It's what you do to make something angularly accelerate. What's the mass? It's the property of matter that resists accelerating. What's this moment of inertia? It's the property of the object that resists a rotational acceleration. So we'll come back and define those in more detail later. For work, we're going to have rotational work. And instead of force, it uses torque. And instead of delta x, it uses delta theta. And there's not really a cosine of theta on the rotational work. For net work equals change in kinetic energy, well, now this is translational kinetic energy, and if we have rotational work, we're going to have rotational kinetic energy. So remember, kinetic energy is the energy something has when it's moving. The more mass it has and the faster it's going, the more it can, it can hit something and do work on it. Well, when things are rotating, they also have energy. They can do work. If you don't believe me, just get someone on the exercise bike, and when the wheel's spinning really fast, just try to stick something inside the spokes, and it's going to do a lot of work on. Don't stick your finger in there. Stick a straw or something. So there's rotational work, rotational kinetic energy rather. So this over here, what we just called kinetic energy before, is called translational. Translate just means move from one place to another, okay? So translational kinetic energy, and we have that's the old stuff. And now we have rotational kinetic energy, which instead of 1/2 mv squared, it's 1/2 times the rotational version of m, which is I, and the rotational version of v, which is omega squared. So it's still, we're just taking the Latin version and translating it into Greek and getting brand new physics. And then finally, the net force equals delta P over delta T. The Greek version of momentum is called angular momentum. And it uses the letter L. That really annoys me because it's not a Greek letter, and I really want this to be perfect to go from Latin into Greek. But we don't, for whatever reason, we don't use a Greek character lambda for angular momentum, or at least most people don't. But so L is the rotational version of momentum, and it's equal to the rotational version of mass I times the rotational version of omega, of velocity omega. Okay, so that's a complete sort of guide to translating from Latin into Greek. And it's going to take us the rest of this week and next week to really get through all of these equations and all of what they mean and what the applications are. But today we're really going to be focusing only on this equation. The net torque equals I alpha. So a torque is sort of a twisting of something. And this is the one that applies to the human body a lot because we have a lot of injuries that come from twisting. Twist your arm, twist a joint, tear your ACL, pull a muscle, dislocate a shoulder. There's a lot of injuries that occur because of twisting. And the torque is kind of a twisting. So before I go and dig into the torque in more detail, does anyone have a question about this overview? Okay, so let's talk about torque. So torque is, it's how we twist something. So imagine you want to open a door. Maybe there's a doorway, and there's a door kind of looking like that. Okay, and we want to open the door. So here's the doorknob, and we're going to push the door to close it or to open it. That depends which way we push it. So you can think of a door as a rotating object. It doesn't actually move anywhere. It doesn't go from point A to point B. It just rotates on an axis. And the axis is, kind of right through here. Let me maybe make that a different color. There's the axis that it rotates on. So when we push it, we want to make it rotate. There are actually 3 things about how we push the door. Now, normally in a face-to-face class, I actually illustrate this with a real door, so it's a little easier to do that. But there's 3 things about how we push the door that are going to influence how quickly it accelerates. Therefore, there's 3 components to torque. Okay. The first component is, of course, the force. How hard you push. So the harder you push, the faster it's going to swing open. Can someone tell me anything else about how I push the door? Now, I'm focused on how I push, not the properties of the door. Obviously, a heavier door will be harder to open than a lighter door. So I'm not talking about the door. I'm talking about me. What else about how I push the door influences, helping it open quickly versus, or having a big effect versus a small effect? Anyone have an idea? Ziad?
It's like maybe like leaning into the door as you try to open it.
Could you say that again? I couldn't quite hear you.
So like trying to leaning into the door when you're trying to open it.
Leaning into it. So by leaning into it, I think you're saying give it more force.
Yeah.
So that's true, but I'm already kind of counting that. But there's something else that does not involve how hard I push, but still influences it. Can you think of something else? Danielle.
Maybe the angle or how far you push it open?
Okay, so those are two different things. How far I push it, let's start there. What do you mean by that?
Like, I guess I was kind of saying it as one thing. So if you push it further, then it would be a bigger angle. So I guess the angle that it's open at.
I'm not. Can you tell me more about what you mean by push it further?
I guess from longer, it would go.
Do you mean to make it move a longer distance, or?
Yeah.
Okay, so to do like this versus just that.
Mm-hmm.
Is that what you mean? Okay.
Yeah.
So that is going to really come about more when we find delta theta, which would be, omega naught or omega initial t plus 1/2 alpha t squared. So what you're talking is about delta theta, and that will be influenced by how long I push and how big the acceleration and if it's moving at the beginning. But I'm really just focused on the things that are going to affect the acceleration. So it's connected to the acceleration, you're right, but I'm thinking more cause and effect. What is the thing that will cause it about how I push, that will cause it to swing a lot versus just a little, other than how hard I push?
Mass.
The mass?
Yeah.
Yeah, and so the mass is going to be involved in the moment of inertia. So these are all, you're right, they're all things that affect it. So we have net torque equals I alpha. So the mass is affecting this, but there's still more that affects the torque. That's not part of the mass. It's not part of the size or shape of the door. All that would be inside of the moment of inertia. But it's really about how I push. Like, for example, can you think of a way to push that door that would be to push it really hard, but it wouldn't be very effective? Anyone? Okay, how about if I just push the door like that? Would it make the door swing really fast? I don't know if you're saying yes or no. Who thinks, raise your hand if you think pushing the door like that will make the door move really fast. No one's raising your hand. What if I push the door like this? Raise your hand if you think that will make it move fast. Okay, so there's differences. Those two forces are the same size, but there's something different about those two forces. What's different about them? Kat?
The direction.
Yeah, the direction. What could you say about the direction that you want to push to have the maximum effect?
You want to push it like with the direction of the door's angle.
Okay.
I don't know how to say that right.
Yeah, you're saying this one, right? This one makes a right angle with the door, then it's sort of along the line of the motion the door makes, right?
Yes.
Yeah, so the angle is the second factor. The angle you push the door. Now, this is actually kind of hard to think of unless someone points it out to you, because we all know so clearly that you always push a door at a right angle, right? because another angle doesn't really do the same job. And by the time you're, under 2 years old, you already know how to open doors. You push them at a right angle to get, make it the easiest. So it's hard to think of it. And there's one more thing about pushing the door. That's not the angle. That's not how hard I push. And again, it's something we already know what we should do. So it's hard to think about pushing the door the wrong way. But there's a third thing that influences how quickly the door will open. Can anyone think of what else about the force vector, not how big it is and not the angle, could affect how quickly the door closes or opens? So suppose I'm pushing at a right angle, and I'm pushing with the same force. Is there anywhere else I could push staying at a right angle that would be not so good? How about if I come up and push the door right there, but at a right angle? Will the door, raise your hand if you think the door will swing closed really fast. Raise your hand if you think the door will swing closed really slowly. Okay, so can someone articulate, what's the difference between those two pushes? Why one is better than the other? Ziad?
So like if you push closer towards, I guess that would be where the joints are for the door.
Mm-hmm.
You would not really get a lot of movement. Like you'd be pushing. I don't know. Actually, it's kind of hard to explain. But, like it would be slower because you're right against those joints where the door attaches to the wall.
Right. The way to explain it is to say you get less torque. That's what the words you're searching for. We just don't have that concept in our language very well yet. But you're absolutely right. If I push close to the hinge, I don't get as much effect, right? It doesn't create as much torque. And so we call that R. And I'm going to draw a picture in a minute to sort of, but it's the distance. From the distance from the pivot point or from the axis of rotation. So the farther we push away from the axis of rotation, the more effect. I encourage you to just try this out after class. Next door you come to, try to open it just pushing maybe 5 inches away from the hinges and see how hard you have to push to get the door to, open at a reasonable rate. And also try it at a weird angle. Try an angle that's not perpendicular so you can see what effect. Now anybody, if you're working with tools and you're trying to, loosen a bolt or something like that, that the longer your wrench is, the easier it's going to be. That's also related to creating more torque, as we will see. So if we would look at the door from kind of a top view, so here's the door handle, here's the door handle on the other side, and here are the hinges of the door, okay? And we just decide to come up for whatever reason, and we push the door like that with the force F. So that's not the optimum place to push the door. The optimum place would be close to the door handle, and the optimum angle would be to make a right angle. But suppose we don't do that. We then have a vector R that defines the distance from the pivoting axis to the place where I apply the force. And in that regard, if I kind of extend the direction of R, there's an angle defined between the angle that R makes and the angle that F makes. So the formula for torque is equal to R times F times the sine of theta. Okay, so those are the three components. How hard we push, where we push, and what angle we push. And it's possible that you push very hard but get no torque whatsoever based on a bad choice of the angle or a bad choice of R. Like if I push just on the hinges of the door, it will never rotate. And if I'm only a couple of inches away from the hinges, I'm going to have a really hard time. Okay, so what is the sine of theta doing? It's basically giving us a component of F. This would be F times the sine of theta. It's giving us the component of F that's perpendicular with R. That's really the key feature. R and F, if they're perpendicular, we get the maximum torque, and if they're not perpendicular, then we need to find how much of the force is perpendicular, because the piece of the force that's along the line of R, it doesn't cause rotation. It doesn't rotate the door. Only the piece that's perpendicular. Okay, so that's our definition of torque. Any questions about that definition? Okay, so let's go ahead and take a short break. When we come back, we'll do some examples with torque to see how to compute it, and see what's going on, and then we'll learn how we're going to apply that in this chapter. Okay, so maybe 5-7 minute break, something like that.